of School of Arts and Science VMRF, I welcome you all to the fourth day of International FDP under the title of Exploring Innovations in Mathematics and Statistics, conducted by the Department of Mathematics. And the resource person for the day is Dr. Kanendra Naidu, presenting on the topic Optimization in Power System. To introduce our presenter to the participant, I request Dr. V. Anandan, HOD of Department of Maths, to do the honors.
Thank you, ma'am. Good evening, sir. Dr. Kanendra Naidu has completed Diploma in Electronics and Information Technology in the year 2002 to 2003. He has also completed International Advanced Diploma in Computer Engineering in the year 2003 to 2004. He has also completed Bachelor of Engineering, Electrical and Electronics, UCSI University in the year 2005 to 2008. Dr. Kanendra Naidu completed Master of Engineering, Electrical Energy and Power System in University of Malaysia in the year 2009 to 2011. Dr. Kanendra Naidu is awarded PhD in University of Malaysia in the year 2012 to 2015. Dr. Kanendra Naidu has published 18 papers to various corpus index journals. He has presented 11 papers to various conferences. Dr. Kanendra Naidu has received a Star Scholarship Award for Diploma and Advanced Diploma in Computer Engineering, majoring in Electrical. He has also received a Star Scholarship Award for Bachelor of Engineering. Welcome, sir. Hello, sir.
Thank you, sir.
Thank you, ma'am. Thank you. Sir,
Dr.
Kanendra,
Kanendra,
sir. Sir.
Dr. Kanendran sir, please unmute yourself, sir.
Hello.
Hello. Hello.
Sir, you are audible.
Yeah, audible, sir.
Yeah. Can you hear me?
Yes, sir. Here, sir.
Okay, all right. Sorry for the technical difficulty. First of all, a very good evening, and also thank you
Yes, sir.
to Professor for the very kind introduction. I'm very honored to be here today to share, I would call a knowledge sharing session within my expertise on nature-based swarm optimization for power system problems. Right. So without further ado, I'll start my presentation. Right. So this talk outline, we will go into an introduction of why optimization is important, and two very notable optimization technique, PSO and ABC, and application in engineering in general, and also I'll go a little bit into the application in power system. Right. So what is optimization? So currently a lot of research or undertakings are being done in optimization field. So basically optimization is you're trying to maximize or minimize a certain function. This function is bounded by its range. So what do you do in optimization is you keep on repeating the process until you get the optimum solution. And the next question is, why do we need to optimize? So the reason why we need to optimize is we want to get the optimum parameters, whether it's a design problem or it is a problem of choosing certain parameters, or if it's a problem of tuning, and also the problem of selecting certain equipment, the power rating and so on. That is the reason why we need to optimize. And also at the same time, we want to make sure that the system output or the system response is giving the best response. So the best response can be categorized in a couple of ways. So how do you say the system is giving the best response? So in engineering, in general, what we do is a system that gives the less error, or the system which gives the users the less cost. Or you can also say a system that gives the maximum profit, or also a system that can give a maximum output, power output or whatever output, depending on the nature of our problem. So that is the reason why we need to optimize. The next question is, we already know what is optimization, why to optimize, how do we optimize this? So optimization, there are a couple of methods. The main two methods would be, the first one is through equation. So in order for you to do an optimization through equation, you need the mathematical relationship between the input and the output. So there's a lot of mathematical problems which can be optimized. Or if you have a system, whatever system it is, it could be an engineering system or whatsoever, that system has to be written in terms of equation. So in terms of equation, normally if you see for engineering problems in particular, they will use ODE, ordinary differential equation, to represent the whole system. So if you are able to obtain the whole equation of one whole system, then you can do optimization based on the equation. The second method is through simulation, based on the engineering model. So in an engineering model, could be from many different ways. For example, so for example, simulation could be from your software. An engineering model could be different software such as NCS. NCS is a very famous software for engineering, and also could be MATLAB or any other software that is able to give the model of the system. So this is why optimization is very important. And another question you have to ask is every problem optimizable? Do we need to optimize every problem? So you have to go back to your application. If your application do not need to optimize, then you don't need to optimize. So this is a general optimization problem, nonlinear equation. So from that equation, you can see you can actually do minimization or maximization. So minimization and maximization is just the inverse of each other. You put a negative, it becomes a maximum problem, or you put a positive, it's a minimum problem, right? So that is a general statement for how we do optimization problem. So whenever we want to optimize, we need something called the objective function. And the objective function basically is the function that relates the input and the output. And at the same time, in any optimization problem, you will be subjected to constraints. The constraint can be inequality or equality constraint. And sometimes when you solve a certain problem, even though you're able to get the answer, that answer is something that you don't want. Why? Some of the application of optimization, for example, you get an answer of for a battery size of negative. So a battery size of negative is something impossible in real world, negative kilowatt. So you don't want that answer. So what you need to do is that you need to put a constraint saying that anything less than 0 or less than 1 is not feasible. Similarly, for certain equipment or design, when you get an answer which is not available in practice or real world, so we will say we don't want these answers. They are, we can put a constraint to say that these answers are not applicable, right? And sometimes in optimization, you have to round up the answer. So certain equipments or certain components, they sell in tens or hundreds. If your optimization give you answer of 2.315 in decimal points, you cannot find that exact component. So sometimes you have to round off the answer to the nearest, right? And another thing I would like to stress is the terminology of best and optimum. So best means it could be best based on the time or best at that particular instant. But optimum means it's the best of the best. Means if you say that is optimum, there is nothing better than that, right? So why do we actually go with the optimization when you have some of these functions, especially non-linear functions, they could be very difficult to solve to obtain the minima, especially a long differential equation, which is very complex. Yes, perhaps you can solve, but it will take a very long time. So when we are doing a system, for example, a complex engineering problem, when we want to represent in mathematics, it is very time consuming because everything is interconnected and the time taken is too long, and it is a bit difficult and complex to solve. There are many methods you might heard of, linear programming, MILP, mixed integer linear programming, and so on. And sometimes these kind of mathematical models, as I mentioned, it will be hard to integrate. And for you to find a solution, it will take a long computation time. And they have special solvers for this. One is IBM Cplex. So they used to solve this kind of linear programming problems. Then you have the NP-hard, NP-soft problems, and so on. And sometimes the solutions are heavily constrained that even to find one answer is so difficult, let alone we want to find an optimal solution. So if you look at the graph on your left, you can actually see the terminology of local minima and global minima. So what we want to find is the global minima. But what happens is sometimes when you differentiate using gradient method, you get stuck in the local minima. So why do you get stuck in the local minima? Is because during the local minima, when you start to differentiate, it will also end in 0. So when it meets a 0, the technique will tell you, or normal conventional technique will tell you, okay, the answer is found. It's already 0, means that is the lowest point. But looking at the function, you can see that there is another minima which is lower than that, but at a different place. So how do you go there? So that is what optimization try to help. And similar to local maxima and global maxima, right? So sometimes you get stuck in the local minima or maxima. So you have to find ways in certain optimization to escape. You want to find the global minima. So these are two type of functions, and you can see from these functions, which are actually we have the XYZ coordinate, and it's quite complex to find the minima, because if you look at the bottom part, there is a lot of minimas, and sometimes certain function can have more than one global minima, right? And these are some examples of functions. There are a lot more functions which are used to test optimization problem or optimization technique. So if you propose a technique, IEEE will have 25 or I think maybe it would be 30 functions where you have to solve. They'll give you the answer and see whether you can find the answer or not. So the dimension of the problem also matters. So in engineering problems, you will have problems with high dimensions. We are talking about 8 dimensions, 9 dimensions, because you have a lot of components in the system. And another problem is these are all conventional optimization. You also have discrete problems. So in discrete problems, it is not continuous. You wouldn't have a very beautiful curve or so on. It could be infeasible for a couple of 100,000, and then suddenly you get a feasible solution. So discrete problem is also a big issue in power system or engineering, and people have actually modified this optimization to become discrete optimization to solve discrete problems. So the application of optimization in various fields of engineering, we minimize power losses in transmission line, and in aeroplane we try to design the most efficient aerodynamic shape of the fin, of the wings, of the rotor. And in terms of construction, civil engineering, we can design the fishway. And even in civil engineering or structural engineering, to design the water runway in hydro dam, right? So where is the optimal location of the spillway and so on. In telecommunication, when you place the towers of these telecommunication towers actually cost money. So how do you want to place it in a optimum way so that you reduce costs? So we can use optimization. And also in telecommunication, when you have networks, radio networks or mobile phone, they'll have EMF generated, and they will tend to interfere with each other. So how can you design such way that they are close but they are not overlapping? Again, you can use optimization for these kind of problems. So there are different types of optimization. If you go on any literature, you'll find thousands of techniques in optimization, and all these optimization techniques are based on phenomena that we observe happening around us. And in optimization, there is heuristic and meta heuristic. Heuristic means knowledge base. So fuzzy logic, expert system, those are all heuristic approaches. Then you have meta heuristic. Meta heuristic means half random, half based on knowledge. So in optimization, we have population based, and then we have nature inspired. In nature, we have swarm intelligence, which is PSO, ABC, FA, CS. These are all based on nature. Particle swarm, artificial bee colony, firefly, cuckoo search, bat algorithm, gray wolf algorithm, a lot of algorithm. And evolutionary algorithm is based on human evolution. You have genetic algorithm, uh, evolutionary programming, and even ICA, imperialistic competitive algorithm. So there's a lot of algorithms. These are based on nature. Similarly, there are some algorithms based on physics. So physics-based algorithm, algorithms such as gravity search algorithm. Then you have voter selection algorithm. So yeah, there are a lot of algorithms. Each of these techniques are different. So you have to see which technique fits your application. There is no one technique which is good for everything. No universal technique. So it's all application dependent, right? Okay. Right. So I will enter into particle swarm optimization, PSO, and I will go through the structure a bit and explain how PSO works. So PSO is developed by Kennedy and Eberhard in 1995. And what it does is that it tries to simulate the behavior of movement of organism. The organism we are talking about here is based on the bird's fly path and how the birds will actually converge to the optimal position. So in the graphics below, you can actually see that initially when it started, all the particles were random, and slowly they will iterate and move to the optimal solution. So finally, all the particles will converge to that one optimum solution or your global minima. So all of these algorithms will have their own parameters. In particle swarm optimization, we call it population, which is the swarm. And the candidate solution, we call it particles. And the group of particles is one whole group, is one swarm. And how do we update the solution? We actually update based on velocity and accelerating components, cognitive and social information. So basically, these parameters we have to define what is the population size, what is the dimension, what is the iteration. So based on this, we can update at every iteration to find the global best, G best, or they call it global best. And during each iteration, your particles would be mutated. Okay, they mutate, and then it comes the final solution. So you can see in iteration 0, all the particles are random, and the star down there is the final solution. And after a certain number of iteration n we say, it goes to the global solution. So this is how an optimization, in this case PSO, works. And if you look at this function, which is based on the earlier function of x squared plus x times cos x, if you were to give a range from -10 to 10, the x is -10 to 10, this is the graph or the figure of that particular function. So when you plot this figure, you will find that the particles are the x and the y is the fitness, or y is your answer objective function. So what we want to find is the global minima, as you can see, which is the fifth particle, which is x equals to 9.66 something, and y equals to -100. So that is the lowest point in this particular problem. So this is a general structure of a PSO. So there's two phases. The first phase is called initialization phase. The second phase is called the iterative phase. This phase or this process find the global minimum. So initially you have to generate random particles. You generate random x, right? So you generate random x, and from this x, you evaluate the objective function to get the y. And from this set of y, you can already know, you can rank them, you can arrange them in ascending or descending order, depending if it's a minimization or maximization problem. And then you enter into the iteration, a while loop. So it could be a while loop or a for loop or any loop. Basically it's iteration, and inside the iteration you update the particle velocity. So that means the particle moves. So there's a formula for the velocity which I'll explain. So when the particle move, you update the particle position and you get the new best particle, and then you select the best particle. So you keep on updating the y, the best y. So for example, in the first iteration, in the minimization problem, you get y equals to 5. Okay. The second iteration, you get y is 3. So 3 is better, lower than 5. So you update y is 3. The third iteration, you get y is 10, and 10 is not good. So you don't update. You remain with y is 3. Then you go to the fourth iteration. So this is how the optimization works. Is this a random process? No, it is not a random process, because we don't randomly generate the particles in the iterative process. There's a formula. So these are the three basic steps, the primary structure of PSO. So evaluate the fitness of each particle objective function. You have to calculate velocity and update the particle position, and then update the individual best and G best. So this would keep on occurring until you reach the maximum iteration. So the question now is, what is the maximum iteration? So there is no fixed answer. Certain application, you see, they use 1,000 iteration. Some might use 100 iteration. Similar to the particles, how many particles is the best? Some will use 30 particles, some use 100 particles, some use 60 particles. So it is always application dependent, as there is no fixed number for this. It is, you have to look at your problem. If your problem is too complex, it requires a long time to solve, then you need higher number of particles and higher iteration. But you have to remember that when you do this, the time taken will increase. So the particles are random numbers based on dimension, and is bounded by the range. Either you want to solve one problem, two problem, or 5x, 5 problems, meaning you have x1, x2, x3, x4, xy. So we call it 5-dimension problem. And the Y is 1 because we are talking about single objective optimization. There's also multi-objective. I will touch a bit later, but always remember we are talking about one Y and multiple X. So the velocity update, it has the velocity component, acceleration and initial weight. And acceleration have cognitive and social parameter. And why do you need this velocity? This velocity function is the one that helps the particle to reach the global minimum. So this is the function or the relation equation of the velocity. So as you can see, Vk plus 1 basically means the particle at the next velocity. Okay, the next velocity, what is the value is based on the current velocity and also a function of the current particle position x1, xik, and also the best solution. So this is the relationship that relates the particle position to the updated velocity. And then looking at the inertia, so the first one is the formula at the bottom, which is Wk, where we take the inertia max minus mean divide by the iteration. So the inertia coefficient is between 0.8 and 1.2. And why do we need to do this? So that at every turn, it will guide the particle to move into the final solution. So this is where the inertia comes into play. So this is your initial weight. So every iteration it will update. Next is the cognitive function, which is the acceleration constant. This one helps explore the search space. The value is between 0.7 or 2. So usually people use 2. But again, as I mentioned, there's no fixed answer. It could even be 0.7 or some have used 1, 1.2. It's based on what people have researched for their problem. And what acceleration constant does is that it is exploring the search space. So what is the meaning of exploring? Exploring means you go to different place to find the best answer. Look at which particle gives the best answer. The next one is called exploitation. Exploitation is based on the social parameter, and this helps the particle to exploit the search space. So exploit the search space mean compared to exploration. Exploration means like you're going big, you're going to different areas. Exploit means you're in the same area but keep on finding even more. You keep on digging in that same area. You're not going to different area. So this is very important. These two different processes, exploit and exploit, is very important. And it will move to the best region or the best answer that we want. So the value is also between 0.7 or 2. People have used either values depending on your application as well, right? And this is a PSO flowchart. So if we go through the flowchart, when we start, we have to initialize the PSO parameters. So what you have to initialize? You have to declare the number of particles, the iteration maximum, the dimension, the upper bound, lower bound, the range. And just now I showed you the inertia, C1, C2, the social and acceleration parameter. All of these have to be defined. What are these values? So once you have defined this, then you go to the next step, which is generate the swarm. So generate swarm, you generate your X. How many X you want to generate depends on your number of particles, 20 or 30 or 10. And how do you generate random numbers? Depending on the software that you use. Software like MATLAB have the random function. It can generate random number. If you're using Python, perhaps there's a library, or if you're using C++, you can take the CPU clock time and then generate random values. And then you evaluate the fitness function. Fitness function is your Y. So with different values of X, what are the Y values? Update the personal best value the particle, the X, the best X and the best Y, you update. Then you move to the termination criteria, which is your loop. Let's say you set for 200 iteration. So the first one is number 1. So you never met the termination. You calculate the V, the velocity, update the X, means now your X have changed, right? The V you have calculated, now your X have changed. So then you repeat, you can see the arrow, you go back, evaluate the fitness function again, and keep on doing this step until you have met the termination criteria, which is whatever that you have set, 200 or 500 and so on. Then using this, you can say you have find the answer, which is the final answer that you want. Right, so that is on PSO. Next, perhaps I will explain a bit on the artificial bee colony. So artificial bee colony is another optimization process which is used quite a lot in a lot of applications. So based on what the name says, it is developed by D. Karaboga in 2005, and it's one of the most, I would say, a famous optimization technique because it is very strong, and it is motivated by honeybees. So how the bee finds the food source with the highest nectar. So it will go to the flower with the highest amount of nectar, and how the other bees will know that is that flower. So that whole process, they have made it into an optimization process. So ABC parameters compared to PSO parameters that you saw earlier, it has different terminology. We use population for colony size, and candidate solution is called the food. And this particular optimization have 3 phases. So I will show you the structure. It will have 3 different phases. The phases are called employed B phase, onlooker B phase, and scout B phase. So employer and onlooker are based on experience. So this is exploiting. But the scout B phase is a random phase. So this random phase is called an exploration phase. So every iteration we will evaluate the objective function. So mathematically, what is going on is, in the first, it has 3 loops inside. There's one big loop and there's 3 processes. The first 2 loops or the first 2 processes are exploiting the current space. But the third phase, which is the scout B, is a random phase. So for example, your X is, let's say initially is 5, 4 and 3. And then in the next iteration, it becomes 5.1, 4.2, 3.9. You know, something like that. It keeps on going in that range. But this scout B phase will be totally random. It suddenly will go to X equals to 15. The reason why they are doing this is that they don't want your optimization to get stuck in the local minima. There are chances that it will find a better answer in random somewhere else. If the answer is not good, it will just forget it. But if the answer is good, then they will all go to that particular answer, right? Similarly, instead of particles, we call it food. For ABC, we call it food. And this is the 3 phases which I talked about. So again, you also have 2 phases: initialization phase and then iteration process to seek the global minima. So the first one is the employed B phase. We generate the food and calculate the nectar. And second phase is called the onlooker B. Again, you generate food, but this is based on a probability value. So you can put a probability function and then also update the best food. The third phase is, if there's no updating in employed and onlooker, a counter will be hit. And then if the limit is reached, we go and find the we call it the scout B phase, to find the explore for better food source. So 3 basic steps: evaluate objective function for each food, calculate fitness for every food, and update the objective function. So again, you repeat 100 or 200 or 300 times until you find the best optimum answer, or you've reached the maximum iteration. So this is the formula to update the food, and you can see this formula is a bit more shorter or easier compared to PSO's formula. And the probability function is a basic probability function. This is an updated probability or improved probability. You can also use a normal probability function to see whether to go for the onlooker B phase, right? So basically it's taking the X value and subtracting with the best X value to get the final answer. So basically those are the reason for optimization, as we covered. What are the need for optimization, what are the techniques of optimization, and 2 of the very famous algorithm, which is PSO and ABC, which are widely used for engineering problems. And I will show you one of the application that we have used in engineering. So one of it is called loop antenna design. So this is used in telecommunication. So loop antenna is basically an antenna which is looks like a loop. Okay, it is round, and it has a gap for the terminals for you to connect. And this is the basic formula. The thickness of the loop is based on the diameter of the cylinder, based on this particular equation. So D is the diameter, and obviously R is the radius. Okay, and here when you change the value for the radius and thickness, the design of the antenna changes. And when the design of the antenna changes, the return loss also is affected due to the radius and thickness. The issue here is that this antenna is quite a very simple antenna, and it's being used in many applications. But the question is how to find the optimum radius and thickness to get the return loss. You want to minimize the loss on a certain frequency range. For example, we are looking at the band of 50 to 150, or maybe 80 to 120. So who decides this is the engineer who is designing this solution. So here, as you can see, we have changed the thickness and the radius from 0.64 to 0.7, and you can see the shape of the antenna have changed. So when the shape of the antenna have changed, you can see that the return loss value is also impacted. From 6.3215 becomes 5.5674. And this is just randomly we put in value, and then we put another value, 0.5 and 3, and you can see the antenna becomes very big, obviously, because you've increased the thickness. And you can see the return loss changes, and you can see the magnitude or the mode plot of the system response. It changes as well. So in this particular application, the telecommunication engineer wanted something with the least return loss. So what you need to do is, you know, the boundary, how thick it can be, or what is the radius, what is the upper bound and lower bound, upper limit, lower limit. You set, you make, you use this in PSO, and let PSO decide where is the optimum answer. So to optimize based on these parameters, radius we took 0.1 to 0.9 millimeter, thickness actually 0.02 to 0.1 millimeter, and then you find the optimal solution to ensure the return loss is minimum between 50 megahertz and 150 megahertz. So when we use these values and feed into PSO, it gives the answer of the radius should be 0.7851 millimeter, and the thickness should be 0.0626 millimeter, and it gives the loss of 5.6229. And on your right hand side, you see one graph. This is called a convergence graph. So you can see that at the bottom is the iteration, but I only run for 10 iteration. As I mentioned, that could be 100 or 150. And you can see initially for the 7 iteration, the answer was 5.636. But as the what you call the optimization process occurs, it finds a better answer, which is 5.624 or 623. It is somewhere in between. So it drops. So this is what we call a convergence graph. So in any problem, optimization problem, it should converge. If your line is just straight, all the way straight, that means your optimization did not work. The problem did not solve. Okay. Okay, this is another problem, which is also quite an interesting problem. This is for robot arm or robotic arm. This is called upper limb rehabilitation for stroke patient. So basically they use this particular robot, and this robot will fit. It's like a skeleton, exoskeleton, and then the stroke patient who has problem with the moving the arm will wear this exoskeleton, and it will move to help the patient to move the hand, to trigger back the mechanism, his natural mechanism. Manually people do using physiotherapists to raise the arm, but this is through robot. But the problem with this robot is that you have to make sure the joints, which are all motors, should not jerk violently, because if it jerk very fast, the patient's arm will be injured, right? So they have motors. So how does optimization solve this? So optimization, this is the real robot that we have worked on. Okay, so it's a working model, and then this is the transfer function of the working model. So based on the transfer function, we have the Laplace equation, a Laplace transform of the whole motor, because all these servo motors and the connection between them can be represented using Laplace transform. And then we use optimization to optimize based on the objective function. The objective function is we have some criteria so that it doesn't jerk violently. It will move slowly, so the patient don't get injured. And over here we have used PSO and ABC, and you can see the flowchart of PSO and ABC as what I showed earlier. First you initialize the parameters, then you evaluate, and then you see the objective function and enter the iteration, and then you update the iteration until you get the optimum parameters for the controller. So PID controller will have PIN, KP, KI, KD, the gains of the controller. So that's what we want to find. And similar to the ABC, you can also see, as I explained earlier, there's the onlooker B, employed B, and then you should see the scout B phase as well. So they are moving until they find the optimum iteration. And after they get the optimum iteration, they get the optimum tuning values. So this is the limit of the upper and lower limit of the KP, KI, KD, which is the gain of the controller. And these are the objective function on your right, ISE, IAE. These are all error functions. Integral squared error, integral absolute error, integral time squared error, and integral time average error. So different errors. And at the table below, you can look at the performance of PSO, ABC, and also the last one is ZN. ZN is Ziegler-Nicholas. So Ziegler-Nicholas is a very conventional, it's a very conventional tuning algorithm. And yeah, and from this you can see the cost function And also you can see the overshoot, settling time, and all these parameters of control system. So if you do control system, you would uh, might understand certain of these parameters. But what I'm trying to say is that you want less overshoot, you want but in this problem they want longer settling time. As I mentioned earlier, if the settling time is very short, the patient will get perhaps injured, so they want a longer settling time. So that's how they fixed it, and you can see that PSO PID managed to give a very good solution for this problem. So after they get these parameters, they plug it into the hardware. So this is how optimization have been used in engineering problems, which is a part of power system. And yeah, so the next, maybe I will share some problems in power system and how optimization have helped in power system. So we have a lot of problems, and most of these problems are very mathematical in nature. Um, the engineering, they just apply the mathematics. We don't go into the formulation of the mathematics. So one of it is called the economic dispatch problem, and optimization has been used. So economic dispatch is you want to find the uh, power optimal output, but with the lowest fuel cost. And the next one is called a unit commitment problem. So unit commitment problem is you want to schedule generators so that your production cost is minimized. So when you want to schedule the generator, you have a lot of generator. You have hydro, you have gas, you have coal, perhaps you have nuclear. So how are you going to schedule which generator to kick in the power plant? So again, you use optimization. In optimal power flow, you want to generate power in such way that you want the lowest transmission loss. So that is called OPF. Also optimization is used. And also reactive power dispatch, optimal reactive power dispatch using VAR capacitor, or you adjust the transformer tab. So what are the parameters or what are the values you're going to you switch your VAR, or what is the VAR compensator value? Use optimization techniques. Control and stability, as I mentioned earlier, has been used a lot in controlling generators. As you can see, we can control the load frequency controller to get the less settling time and overshoot. And we also optimize AVR, automatic voltage regulator. In network reconfiguration, currently in distribution system, people have used optimization. It is applied and they have solved some problems. And others are DG sizing. DG means distributed generator, how you want to size your solar panel, how you want to size your wind turbine, and where you should place the wind turbine, or where you should place the solar panel in the network. That is also using optimization technique. And also filters. You have a lot of non-linear filters, or active filters, or passive filters. How do you determine the L and C, inductor and capacitor? So that is a problem, because depending on your system, the L and C value would change. So you can use optimization to solve this problem. So the first one I would talk about is distributed generator, DG. Some call it decentralized generator or dispersed generation. These are all small plants which are connected to the distribution network. And you want to find how many DGs you can install, and what is the optimum location of these DGs. Do you want to put single DG, or you want to put multiple DG inside your distribution network? So when you do DG sizing problem or DG location problem, you have to look at your local network and see how you can integrate your solar or wind to support or sustain your network. So you can see this is a simple 16 bus IEEE distribution test system. Um, those are the main feeder. And then you have the one in the numbers are the load buses. So let's say you can only put one DG and you put the power limit between 0 and 1. So when I say 1 DG means dimension is 1. And when I say DG power limit is 0 to 1, that means the upper limit is 1 and lower limit is 0 megawatt. So yeah, 0 to 1 megawatt. But as I mentioned earlier, if you don't put the limit, you get negative megawatt. So that is not practical. And we want to make sure the power loss is minimum. As you can see, when we calculate, once we have optimized, this is the total loss and in megawatt and megawatt, which is your active and reactive power. So we can play around with the size of the DG to get the lowest megawatt and megawatt. Another problem where optimization have been used quite prominently is direct power control of three-phase shunt active power filter using the PSO algorithm. So over here, as you can see from the figure, this is a power grid, and inside the power grid you have non-linear load and an inverter. And what we want to do is that we want to control the switching so that we get the best power quality improvement. So inside the switching, we have PI controller. So we want to tune the PI controller. And here you can actually see the electronic schematic of the active power three-phase shunt active power filter. And you can see at the bottom there is the proportional integrity controller, proportional integral controller, the PI. So this PI controller will influence the output of your shunt active filter. So what are the values you have to set the gain of your PI? Okay, so this is where you use PSO or any optimization technique. In this problem, the researcher have used PSO, and once you get the value, you can program this value into your control card. If you have a control card or you have a data acquisition unit, you program these values. And then you define what is the gain. And you can see over here the parameters which I explained just now. If you remember, this particular problem, the swarm size is only 10. The number of iteration is 100. But if you look at C1 and C2, I told you just now 0.7 to 2. Here, he has used 1.49. Similar for R1 and R2, he used 0.3 and 0.95. So why is this value different? As I mentioned, it is based on application. So the researcher have tried many values and he found these values are the best for his particular problem, right? And this is the minimization problem to get the minimum error. So at the bottom in the graph, you can actually see that is the convergence graph, which I explained earlier with the 10 iteration. You can see here 100 iteration. So the graph looks quite nice. After the 20th iteration, it is saturated, means it has found the answer in the 20th iteration, and up to 100 iteration, the answer remains the same. So this is a good convergence graph, means you have solved the problem. And you can see the difference between the conventional controller and optimization controller, optimized controller. You can see the overshoot is reduced from 14.2% to 1.5%. The THD, total harmonic, is also reduced. And the error is also reduced from 0.10 to 0.01. So optimization has helped in this particular problem. This is an integration of optimization. So basically this means optimization, not necessarily you use it as standalone. You just don't use optimization to solve, but you can use optimization with another problem. For example, neural network or machine learning. So in neural network, you will find that ANN, artificial neural network, has a lot of parameters. Parameters like momentum rate, learning technique, hidden layer, number of neurons. How do you know what is the best learning rate? What is the best momentum? What is the number of neurons? So it is a bit difficult to find out because perhaps people do trial and error or they take from previous reported literature. So we have used PSO to optimize ANN, and then we try to find all these values which will give the best accuracy. Means if we put the LR, MR, and the number of neurons according to PSO, we'll get the higher accuracy. So we have tested it on a fault location problem for underground distribution system. And you can see the difference between a standard ANN, a normal neural network, and PSO based neural network. And you can see the percentage of error is significantly reduced. So the green color bar chart are the PSO ANN for various impedance values. And we have also tested with different learning algorithm. So if you do machine learning, you would know about Bayesian regularization, Levenberg-Marquardt, and so on, right? So these are some of the backpropagation techniques. And PSO will tell you, okay, learning rate for this technique, 0.414, momentum, number of neuron, you get this objective function, the best. So we have tested it and we managed to obtain all these parameters. Some people call it the hyperparameter tuning. So optimization can help you in this case. And comparing ANN and PSO optimized ANN in terms of objective function with published results, you can actually see that for proposed method, which is PSO with ANN, we are able to get the least error for whether if it's a small network, large network, for a single line to ground fault or balance fault. So we are able to optimize the parameters. And another thing I would like to add is that if you go to PSO, in this slide, you can actually see, yes, this formula, right? Some of the research would say that, okay, this formula can be further improved. So you put another parameter, maybe you call it Z, I don't know, maybe a constant or multiplier. And then you find out that it can find the answer far better and far faster compared to the normal PSO. So this is why when you go to literature, when you do literature review, you'll find problems like they will say chaos-based PSO, improved PSO, modified PSO, or some different names depending on the person who did it. So if you are doing a new algorithm, not to say new, you improve the algorithm, so you can call it whatever you want, right? You can put your own name and do it. Or if you go to ABC, people have done this. So you actually the employed B phase, you put in the velocity updating, so that becomes a hybrid optimization, PSO ABC. So people have done that also, where you hybrid the optimization. So as I told you, there's no one optimization which is good for everything. Some will have, some can be fast, but don't give you the the best answer. Some can give you the best answer, but it's very slow. So yeah, totally depends on what you are looking for. So that's why people will tend to integrate 2 or 3 optimization problems together. So basically, I think that will be my presentation on optimization and its application in engineering and power system. So I think perhaps there's any questions I could try to answer. Thank you.
Hello.
Yes. Yes.
Sir, you say a lot of algorithms.
Yeah.
Can you explain me the genetic algorithm, sir?
Okay. All right. So if we go to the chart here. Okay. All right. So genetic algorithm is a part of evolutionary algorithm. So genetic algorithm was one of the very first algorithm uh, that has been used for optimization. It was way before PSO. So how does genetic algorithm works? So genetic algorithm works based on human DNA. It's basically the parent's chromosome. So when you have two parents and child comes out, so the chromosome of the parents uh, will then produce the chromosome of the child. So it will take the best, or it will combine uh, the two parents chromosome. So this process is the formula of it updating the next generation. Means in PSO we call it particle, here we call it chromosome. So it updates, and then it's called reproduction. Reproduction. Then they have another one called the process called crossover. And in some instances you would see the chromosome will mutate and come up with a very weird answer. So when the chromosome mutates in human, perhaps we call it maybe cancer or something, but in optimization it's a mutation, so it will mutate. So the same process like PSO, it will keep on going for various generation. They call it generation, they don't call it we call it iteration, they call it generation. So until the maximum generation is reached, and then you get the final answer. So again it will also use objective function. The terminology will be different. They as I mentioned, use chromosome, generation, parent, child, offspring. And the way they mutate, there is three or four techniques. One is called roulette wheel technique. So there's another three or four techniques where they can actually generate the next particle or the next generation. So that is how genetic algorithm works. So it is based on human DNA production, reproduction.
Thank you, sir.
Okay, no worries. So any other questions I could, uh, or you can even type the
Karan, ma'am?
questions. Hello,
Karan,
yes.
Yes, sir, yes, sir, yes, sir.
please.
Participants, is there any queries? You can raise your hand or unmute yourself and ask the question.
Samville,
Sir, can we move on to vote of thanks? Anandit, sir?
1 minute, ma'am.
Okay,
Samville,
okay.
Samville, Samville is there?
Sam,
Hello. Yeah, yeah.
Samville, Samville,
Sam,
Samville,
Yes, yes. Hello. Sorry. Yeah.
Samville.
Sam, are you audible?
Yes, sir. Yes, sir.
Yes, sir.
Sam,
Sam,
Samuel.
1 minute, sir. I'll call him.
Okay,
Okay.
okay.
Okay, I think so. If that's all, then.
Yes, sir. Yes, sir. Few minutes, sir.
Oh, okay. All right. All right.
Sharon, madam,
Okay, sir. Okay.
you can say
Participant.
about the platform.
Okay. I would like to thank Dr. Kanendra Naidu for the excellent presentation he delivered today. I would also thank our participants for their active participation. Thank you all for joining us today and kindly fill the feedback form that has been posted now. Thank you all.
Okay. Thank you.
Thank you, sir.
Thank you. Thanks a lot. Thanks to
Wonderful.
everybody.